Hi guys, so today we'll be revising physics portions for Essay 1. I will be just waiting for a few more minutes for people to join in and then we'll start. Yeah, so if you have any particular topic to be discussed first, so that let's make this more fruitful, 1.5 hours. So if you have any particular portion to be revisited quickly, let me know. So we'll be basically focusing on magnetism and electricity. So magnetic effect of the current and electricity. Any particular topic you want me to revisit, let me know. You can post it on the comment section so that I can. Uh, Fleming's right hand rule. Fleming's right hand rule. Okay. So we'll take up Fleming's right hand rule. Anything else? So we'll share the screen so that you guys. Fleming's rule. Okay. Fair enough. So let me first share the screen. Yeah. Okay, so let's start. So first topic to be discussed is Fleming's rules. I hope you guys are able to see the screen now. So first is Fleming's right hand rule. And the second is same Fleming's left hand rule. Left hand rule. Anything else? Let's first jot down what else do you want to cover, want me to cover, so that we have everything at one place, and then we'll start off the discussion one by one. Anything else, guys? Yeah. So shall I consider that to be all? So let's understand. Let me just grab a picture of this so that it becomes easier for you to understand. Just give me a moment. So Fleming's. I'll get an image for you first. So I'll pick up a Wikipedia image and paste it here. Yeah. So this one is from Wikipedia. Okay. So basically, what is it? So let's say you have studied magnetic effects of current. And what did we learn? If you broadly see, you have two appliances which can help you understand these right and left hand rules very easily. So, and I'll go by the practical examples, and then you can relate to what is left hand and right hand rule. Always remember, we have two appliances, electrical machines, which are the results, or let's say, the application of whatever we have studied. And these two appliances broadly, help us understand the entire magnetic effect of the current. One is called motor, electrical motor, right? AC motor, DC motor, whichever it is, but this is motor. And this is a generator or an alternator. These are the two basic appliances in electrical appliances which use the concepts of electromagnetism. Now, what is the difference between motor and a generator? So motor, if you see, let's say if I have to, this is a system. So let's say this is a motor. This is a appliance, right? So what happens in this system is we supply energy, and precisely here electrical energy, and some amount of energy is lost in the environment in this process, and some amount of energy gets converted or is used as work. So what is motor? So what is input here? So if you see, input is electrical energy. Input is electrical energy and output is work. Output. This is output. Always remember this diagram. You will never forget left hand, right hand rule. Right? So in an electrical motor, what happens? You supply electrical energy to get work. Or how do you, if you remember your 9th grade stuff, what was work? If you remember, work was nothing but F dot D. That means dot product of force and displacement, right? Now, force and displacement, that means this electrical energy is creating force or generating force. Yeah, in your language, they also, or let's say this is creating another way I can say this, creating thrust. Right? So electrical energy when supplied to the system of motor, what are we getting? We are getting some work. And how is that work produced? Because some force is there which is getting generated because of this conversion of electrical energy into this work, and that is how it manifests. So if you see a fan rotating above you, what's happening? So you're supplying energy and you're getting work out of it. Why? The fan is rotating, right? There is a force which is getting generated. So hence, in a nutshell, I can say there is one use of electromagnetism where if you input energy Q, you will get work. Yeah, this is, and here is a common thing, and common thing is electromagnetism. So electromagnetism is a beautiful property. If you supply some amount of energy in form of electrical energy, in this case, you'll get work. And the most beautiful part is this process is reversible. That is, you can get the other way around as well. So let's now talk about generator. Generator does exactly the opposite. So hence, I'll draw the system of generator. Let me use another color to differentiate. So let us say this is my system. This is my system. Let's say this is my generator. So here, what you're doing is you're supplying work now. So you are doing work on the system. Example, you're rotating a turbine. Okay, you're rotating a turbine. You're rotating a windmill. Yeah, whether it's a steam turbine or water turbine, some turbine you're rotating, and then what happens is some amount of energy is again getting lost to the environment. Some amount of work which you did in form of some energy like heat, sound, whatever. So it goes to environment, and something will get converted into, let's say, electrical energy. Yeah. So here is electrical energy. So meaning is if you do work, that means if you apply force and there is displacement, you do work, and that work when you do on a system, you do work means, let's say when you rotate a turbine. Okay, so you can do it manually or through using the power of natural resources like flowing water or blowing wind or high speed high energy steam. So what basically you do is when the water falls on a turbine, it applies a force onto the turbine, and turbine starts rotating in an environment of electromagnetism. We'll talk about it. And then what happens is you see electrical energy. So if I have to again summarize it, so there is again what is common? There is electromagnetism again. So there is an electromagnetic system, right, where you supply work or you do work, and then you convert a part of it into electrical energy. So if you see from energy to work and from work to energy, right? It is reversible. So this is what, you know, so we say that you can convert energy into work in an electromagnetic system. Similarly, you can convert work into energy. Not 100% conversion is there, that is for sure, but uh, you can kind of change the form in which energy is, right? So here you were doing some mechanical work, gets converted into energy, electrical energy. Example, powerhouses, right? Powerhouses where electricity is produced. And this is example as so many. So electrical motor is one. So if you understand this conversion of energy into work and work into energy, so this in this this kind of a setup we apply Fleming's left-hand rule. What for will tell you, and in this setup you use Fleming's right-hand rule. Now never forget, I have drawn the two things left. You know, so this is the left side of my board. So you remember left hand. This is right-hand side of my board. So right hand. So just a mnemonic to remember. Now, what did I draw on the left-hand side? Motor. So in the case of motor where energy is converted into work, that means energy is used to produce force, is Fleming's left-hand rule. And on the right-hand side, where work is used to form energy, is right-hand rule. Now, what is it? Let's take the picture down and understand. So this is my picture. Let me just take it here. So I'll paste it here. Now, this is my, so what is this basically? So if you see, let us have a magnetic field. So I said that we have to have an electromagnetic system. So let us have an magnetic field. How do we create a magnetic field? These are the two poles of a horseshoe magnet. Okay, horseshoe magnet you have seen. This is, let's say, north, and this is south. Okay, north and south. So hence you now know what are the field lines, magnetic field lines, starting from north and going towards south. This is my B, magnetic field B. Now suppose we are putting a conductor, or let me put a conductor like that. Okay, this is a conductor. This is a conductor present in the magnetic field. Okay, and what you are doing is, now we are considering what? Motor case, left-hand rule, right? So that means there is input is energy. So let's give it some input. So let me say that what I do is I connect this to a power source. Let's say this is V. Okay, so this is V volts. A cell is there of V volt. Now what will happen? There will be current flowing here. Current flowing like that. This is the circuit, and this is the conductor with some resistance. Now, what will happen? So if you see, this is the direction of the current here. Now, if you know the field and you know the current, you can find out what will happen. This conductor will start moving in this field without doing any external work. So let's say we don't need to do anything. Even if you leave it like that, this particular conductor will start experiencing a force. Now, Fleming's left-hand rule help us to determine in which direction the force will be applied, depending upon, so the inputs will be the magnetic field and the current. If you know the magnetic field and the current, you will know the force applied onto the conductor. So what did we learn? Fleming left-hand rule used in where the input is energy and output is the force. So this is the output, right? This is the input. And this is the common thing. It has to be there, without which nothing will happen. Right? So input is electricity, output is force. Now in which we know the direction of magnetic field, we know the direction of electric current. We just need to find out the direction of force. And how do I determine it? So if you see, this is the mnemonic. You remember, 4 finger. four-finger field always, whether it is right hand rule or left hand rule, your forefinger, stretched forefinger will determine the direction of the field. So in this case, the forefinger has to be pointed in this direction, right? Forefinger. Now, the thumb, so these are the three. Thumb is for thrust. So T for thumb, T for thrust. You remember like that. T for thumb and T for thrust. Forefinger field. Thumb is for thrust. That means force. So stretch thumb and the middle finger. If you stretch all of them in mutually perpendicular direction, third is the middle finger. So if you stretch all these three in mutually perpendicular direction, what is mutually perpendicular direction? If you're sitting in a room right now, any corner you take, the three lines or the three walls are meeting at a point, right? The floor and the two walls meet at a point, or the ceiling and the two walls meet at a point. Those three lines are called mutually perpendicular direction, like that. So stretch your fingers in these three directions. So four-finger field, this is the finger. Then while I'm saying it, you guys should do it. And mid finger is for current. So this is my mid finger. So if you see, the thumb will be stretched downwards. So this is the direction of force in this case. Try it out. And if you reverse the current, let's say if in the second case, if you reverse the polarity, and now if the current flows like that, then forefinger field, again, the forefinger doesn't change. Yeah. Current direction through mid finger, now it will be like that, and stretch thumb upwards. Yeah. So all these are 90 degrees. 90 degrees. So hence we say this is my B, this is my I, and this is my F. Understood? So where do we use Fleming's left-hand rule? Again, let me recap. We use Fleming's left-hand rule where electrical energy is input and force is output, or work is output. Okay, again, please remember, I have drawn this on the left-hand side. I discussed motor, and in motor it was electrical energy supplied to get work. For example, fan. Always remember like that. So right, so it will be left-hand rule. Similarly, we can use the right-hand rule. Let me again grab a right-hand rule pic so that I can illustrate. So I will go to Wikipedia and I will grab a pic from. Yeah. So now copy. Yeah. So now we'll discuss right-hand rule. So this is Fleming's right-hand rule. Right-hand rule, very important thing. Now, so what did I say? Here, what will be the input of the system? In the system, I will be supplying what? You remember work I supplied and I got electrical energy. Electrical energy, right? In the case of generator. So what does it basically say? That if you apply force, so again, common thing will be electromagnetism. So let's first draw a magnet, our usual practice. So let me draw a magnet first. So here is my magnet again. This is North Pole, horseshoe magnet, North Pole. This is my South Pole. And I have now, in which direction B is. So this is the direction of magnetic field lines, right? Let it be B. Now again, I'll put a conductor over here. How? Let me put a conductor. And in the last case, the previous case, we had applied a external power source. If you see, there was an electrical power source. So this was the input. I provided some electrical energy, and the conductor started moving under the influence of this magnetic field combined with electric current moving in that magnetic field. Now, the reverse is also true. That means now what I'll do is, so if I start moving this conductor up and down in this field, in such a way that the area swept by the conductor. So in this case, if you take your pen in through which you are writing and move your pen up and down in such a way that the area swept. So what kind of an area will be swept by it? So let's say if I had this conductor with me, conductor, I am just trying to draw it here. So let me pull it here. Yeah. So this is the conductor. So area swept by it, the moment I move it up and down will be nothing but, if I just draw it roughly, so it will be something like that, isn't it? Area swept by it as this conductor is moved up and down in this direction, vertically up and vertically down. What will happen? So if you see, apparently all the magnetic field lines are passing or cutting through this area swept. Now, till the point, the lines are not parallel to the area. Again, I'm writing here. Till the point, the area swept by the conductor, swept by the conductor, area swept by the conductor is not parallel to field lines. Field lines. That means if the area swept was something like that, then it would be parallel to the field lines. Only in that case, leaving that case, in every other case, there will be a current generated in the conductor. So if, let's say, if you hold it through two sides, if someone holds this conductor through two sides and starts moving this conductor up and down in this magnetic field such that the area swept is not parallel to the field lines, then what will happen? There will be a current generated inside it. So there will be current generated inside it. Current generated. Good enough, current generated. So one way is to, what you can do is, and you have done in labs also, connect it to a galvanometer. Connect it to a galvanometer and you will see the deflection. Right? And basis the deflection, you can find out the direction of the current produced. But alternatively, Fleming gave his right hand rule. Right hand rule. And same three fingers, same meaning, only the hand has changed. So what were the meanings, if you remember? Four finger field, F, F, F. Thumb is for thrust or the force. Force. Now in this case, force is the input. Force is the input, and my friend, the mid finger will give you the direction of the current. Direction of the current. Right? In the case of motor or the left hand rule, mid finger or the direction of the current was the input and force was output. Here the force is input and current is output. Right? Let's see that now in this case again. So I'm drawing it here. My four fingers will point towards this right hand forefinger like this. And the force, that is, let's say I was moving it up. So thumb will be on towards the sky. So hence, if you see, the third mid finger will be pointing towards this direction. So this is forefinger, this is P, and this is M. So hence, automatically we now know that the current direction is this. Sorry. Yeah, this looks a little wrong figure actually. Yeah, maybe I didn't notice it, but it is not so. Wait a minute, where did I pick it from? I'll just check from that source. Give me a moment. Yeah, motion magnetic field. Yeah, it's wrong. It's this figure is actually, it is mentioned here I. It should be F, and this should be I. Yeah, they have also done it wrongly. Never mind. But what I told to you is what is right hand rule. Okay. So this will be induced current. So this is nothing but induced. Why it is induced current? induced current, because there was no current before. And when you did this exercise, that means if you allowed the rod or the conductor to go up and down in this magnetic field such that the area swept is not parallel to the magnetic field, then you will see that there will be a current induced, and the current's direction will be given by this right hand thumb rule, where force is, the thumb is the direction of force, or rather you can also say force is or the direction of motion in which the body moves, right? So motion is the direction in which the force is being applied. So hence this is force, thrust, and B, forefinger is magnetic field, and the middle finger will give you induced current. Okay, so I hope this thing is clear. Any other topic you want me to cover so that it becomes easier for you to? Yeah, just tell me another topic and I will. Yeah, anything else, guys? Please tell me, or else I will move on to some other topic myself. I think. Okay, so let us take up some questions, and through that we. There is a question about the direction of magnetic force. Can we write the direction of the force with respect to the question paper? What Rushil is asking in the exam, if a question about the direction of the magnetic force, can we write the direction of the force with respect to the question paper? Yeah, obviously, it depends on the context, Rushil. So whatever is, for example, let's say, um, can we solve some questions on this? Okay, so you want to, yeah. So to answer Rushil's question, it all depends on which direction the magnetic field is, in which direction the applied force is, and hence induced current will be found out accordingly. Okay, can we solve questions on this perfectly? Let me give you a question on this. Let me give you a question on this so that. Question, right? Okay, yeah. Now let us say the ring. This is a ring. So let me draw a proper ring. I have the facility to draw a ring. Okay, so this is a ring. So this is a ring perpendicular to the plane of our whiteboard. Okay, and let us say that we have a bar magnet. Okay, and yeah, let us say this is a bar magnet, and let's say, yeah, this is my north pole. Oh, sorry, north pole. This is my north pole, and this is my south pole. And this ring is, let's say, held constant. Held constant. And what is happening is this bar magnet is now moved towards the ring. Towards the ring. Okay, towards the ring. Now, if you're looking from this side, what will be the direction of the induced current? Clockwise or anti-clockwise? Again, repeating the question. So basically, there is a ring, metallic ring, and this is the magnet. Magnet, north and south poles are given, and it is being moved towards the ring like that. Okay, so you have to find out in which direction, when looked from this side, from the right side of the ring, whether it will be a clockwise or an anti-clockwise direction of the current induced. So application of right hand thumb rule. No current will be induced as the direction of movement is parallel to the direction of magnetic field lines. Is it? So I am moving it. So what are the directions of? So let's say let's draw the magnetic field lines of. Will not these be the magnetic field lines? Like that? Sorry. Something of that sort. Like that? No field lines will intersect. I'm just drawing a rough diagram. So aren't B and F opposite? B and F. Where is B? B and F. Where is F? Okay. So here says no current. Shreyas Gopi says clockwise. And Kritika is asking a question. Any other thoughts, guys? Take a minute. Break down this ring into small pieces, and you can do that, or there is another way also. I will tell you, but try and understand what will be the direction of the induced current. Move the magnet in the vertical axis instead of horizontal, then a current will be induced, right? What if we move the magnet in the vertical axis? Okay, then current will be induced. Yes, current will be induced till there will be a relative motion between the conductor and, see, if you see here, there is a relative motion between the conductor and the magnetic field. Either you fix the field and move the conductor, or you fix the conductor and move the magnet up and down. In both the cases, there will be a current induced. So always remember, what is the criteria? There has to be relative motion between the conductor and the magnetic field lines. So either you fix magnetic field and rotate the conductor, which happens in, let's say, a small alternator or a dynamo in your cycle, or in a power plant where actually the magnetic field retreats, the conductor remains stationary. If you have studied in the power plants, in the big power plants, it's very difficult to move the shaft. So what they do is they rotate the magnetic field instead of rotating the shaft. Rotating a magnetic field electrically is easier than rotating the mechanical shaft. So whichever way you must have a relative motion between what? The magnetic field and the ring. Now, if you see the ring, initially the magnet would have been at a distance. So hence, number of field lines crossing this will be lesser, isn't it? The number of field lines which are crossing. Let me draw a diagram. So let's say, let me just reproduce this diagram. Okay. So okay. Now let us say that you had the same case. Ring is here, and let me copy this and paste it, and yeah. So let's say when the magnet was here, yeah, the field density means the line crossing, the field lines crossing the ring would be very, very less, isn't it? So let's say yeah. So let's say the lines crossing will be very, very less as compared to when this ring is, let's say, here. So basically, you moving the magnet towards the left is as good as you moving the ring towards the right, isn't it? So hence, you are applying a force in which direction? You are applying a force in which direction? You are applying a force in this direction. Keep the magnetic field constant. Okay, and then the relative motion is as good as, instead of you moving towards instead of the magnet moving towards the ring, let the magnet be fixed and you move this ring towards the magnet. So what is happening? If you see, this is the field line, isn't it? So if you take one particular let's say top of this, a very small portion of this ring, okay, let's assume for all practical purposes that is it is perpendicular there, okay. So hence, or for that matter, just a minute, yeah. So basically what happens is, let's say you have a small conductor placed like that, placed like that. Okay, but yeah, here you have to understand one thing, friends. It is not a case of constant magnetic field. Why am I saying that? Because you know that as you move away from north pole, so for example at this point, magnetic point, let's say this is ba, let's say this point is a, so magnetic field strength is ba, and let's say at this point b, let's say p, this point p, so BA and BP, you know that. Do you know that BA is very less as compared to BP? Because closer the pole, or if you're closer to the north pole, the magnetic intensity is quite high. Yeah. So hence, yeah, here is mentioning about lenses, and that's where I was coming to. So hence, what will happen is this will here here we will be using lenses law. Lenses law, and what is that? Now, in this case, what's happening is as you are moving the ring magnet, towards the magnet, more and more lines are cutting the magnetic field. More and more lines are cutting the magnetic field, isn't it? So as you are moving towards the magnet, more and more lines are cutting the magnetic field. Now, Lenz's laws say that this relative motion of the conductor inside a magnetic field will try to induce a current in the conductor. Now, there are only two possibilities of current, either this or this. Let's evaluate each one. Let's say when looked from here, this current is anti-clockwise, this case. And look from the right side, this current is anti-clockwise. Now, lenses say that the induced current will be such that the induced magnetic field because of that induced current will always oppose the inducing magnetic field. Please understand, it's a little complicated in terms of wordings. What I'm saying is, this is my inducing magnetic field. Okay. Now this inducing magnetic field, Lenz's law, will be opposed by a magnetic field produced inside the ring, or produced by this ring, So as this relative motion between the conductor and the magnet takes place, more and more inducing field crosses the ring. That means there will be induced current in the ring. Now the induced current in the ring will create a magnetic field which will oppose this magnetic field of the bar magnet. Now, to oppose this magnetic field of the bar magnet, the ring must create a magnetic field in this direction. Now, how do you get this direction? So you have learned that if there is a current in a conductor, how do you get the direction of the induced field? Sorry, how do you get the direction of the field created by this conductor in the loop? So you do the right hand thumb rule again. So you curl your finger along the direction of the current, and the stretch thumb gives you the direction of the magnetic field produced by the conductor. Okay, so here if you curl your finger in anti-clockwise direction, then the magnetic field produced by the conductor will be towards the right, and hence the current induced in this conductor will be anti-clockwise. Again, why anti-clockwise? Because if it is anti-clockwise, current flowing in the conductor, the magnetic field produced because of that anti-clockwise current will be towards the right, and it must oppose the magnetic field produced by the magnet, and hence it is doing so, and hence my assumption that it is in anti-clockwise direction is correct. I hope you understood this question. Let me take a board question and help you with that. Okay, so I am going to take one board question on, yeah, magnetic field. Magnetic field. Okay, just give me a moment, guys. Mm, magnetic. Magnetic field. Okay, very good. Mm, mm. Okay. Wait a minute. I am just trying to find out. Uh, okay, okay. Hmm. So Vikas is asking, so even if direction of movement of magnetic field is parallel to the magnetic field, direction of movement of magnetic field is parallel to the magnetic field, will a current be induced? Current induced, Vikas, depends on only the relative motion of the conductor and the magnetic field. If it appears that the conductor is cutting the magnetic field lines at any point, then there will be induced current. If the conductor is at no point cutting the magnetic field lines, then we say, and we observe that there is no induced current. Okay, so yeah, let us solve this. So tell me, solve this question. Which one is correct? Hmm. So this is, let's say, question number one. Just to differentiate, this is one, two. So both faces A and B of two bar magnets are north pole, not possible. South pole, not possible. Correct. First one is D. Okay, next. Question number two. Mention your answer as 1D or 2D or whatever, so that I can know. This is question number three. 2. The magnetic field near a long straight wire is described by. This is actually concentric. This is spelling error here. This is concentric circle. Concentric circle centered on the wire. Yeah. 2C, correct. This is correct, and this is correct. Now, question number 3. A is DC. Why? Because current, magnitude, and direction both constant with time. Direct current. And B is AC. Perfect. Name any source of shown by A. Now, source of A. What is source of A? A DC generator. Okay. Best example could be a cell, a dry cell. Yeah, source of A is cell. Okay, what is the frequency of current in case B? Find out the frequency. What is frequency? Number of cycles per second. 50 hertz. Good. So in this case, 50 hertz. Why? Because the time period, if you see, what is frequency? Frequency is given by F in hertz is given upon 1 upon T, where T is time period. Time period. What is time period here? One full cycle. Time taken to complete one full cycle is this 0.01 and then 0.02 seconds. So T equals 0.02 second. So hence F equals 1 upon T equals 1 upon 0.02. 50 hertz. Difference between A and B. What is the difference? You can difference. You can suggest the comment section. Meanwhile, I'll give you another question. Another question. Another question here is this. So, question number 4. For C, yes, yeah, correct. So at the time of short circuit, current in the circuit increases heavily, and this leads to what? Or leads to what? What happens in the circuit? So hence you know that R power, electrical power is I square R. Okay, so hence if you increase the current goes up heavily. So a lot of power is generated. So hence it manifests itself in form of heat, and it may lead to fire. Hence we provide what? Fuse. So that before anything happens, the fuse melts and the circuit is broken down. AC is more dangerous than DC. AC is used. Don't use such statements, Kritika. AC is not dangerous than DC. Okay, so danger is a relative term, so don't use. Actually, DCs are at times more dangerous than AC. So you'll not talk. You'll also talk. You'll only talk in technical stuff, technical terms. So let me just draw the column to differentiate. Yeah. So first, that the magnitude as well as the direction of current changes. Direction of current changes. Current changes. Okay. Here, magnitude as well as and direction stays constant. Stays constant over time. Okay. Right. So produced by a AC generator, or if you see your inverters at your UPS. In the UPS, there is something called inverter. So AC generator inverters will produce AC current. Here, it will be a cell, a dry cell, a battery, or a DC generator, or a dynamo. DC generator. Okay, and as Vikas was pointing out, uh, can be transported or transferred to larger distances by doing what? By stepping up. By stepping up the voltage. Stepping up the voltage or potential difference. There is no possibility of stepping up here in this case. So since no stepping up, so it restricted to or small areas, or transfer is restricted to small areas, smaller distances. Since there is no possibility of stepping up a DC source, hence not possible to transfer to a long. So to transfer to a larger distances, we have to create more power there. Okay. So this and household circuit are AC. Use AC. For example, your refrigerator, your air conditioner, your fan, your bulbs, your tube lights, your geysers, all are using AC. And here it is, electronic items like your cell phone, your laptop, yeah, all your PS stations and all that. Electronic items use DC mostly. So it is AC you will see in high power application, in industries, high power applications. High power applications like running industries, big firm furnaces and motors and all that. Here, these are low power applications usually. Low power application. So don't mind my handwriting. I just try to do it a little bit faster so that you can recap quickly. Is that difference clear? So what did I tell you? Magnitude as well as the direction current of the current changes. But in DC, magnitude and direction stays constant. Here produced by AC generator. So because of the tab thing, So AC generator or inverters. Here it is dry cell, battery, DC generator. Can be transported to larger distances by stepping up the voltage, restricted to smaller distances. Household circuits use AC, electronic items use DC, high power applications, low power applications. Usually. Usually. Okay, tell me anything else I should be covering, or let me also give you some questions from electricity. Okay. Mm, so voltage in AC is stepped up using something called a transformer, Ishan. We will not cover transformer because it's not there in your. We'll take it up in the class separately. I'll give you, when we meet in the class, we'll tell you that, or I can send you a lecture on that after this class. So do this problem. So let us start. Yeah. So transformer is something like this, just for Ishan's understanding. So let's say I have a transformer. Transformer is something like this. So you have a core, soft iron core, like that. Let me draw it properly. Yeah. So this is a soft iron core. Okay. Soft iron core. And on top of it, what you do is you wind some coil like that. This coil is called primary. And similarly here there will be this coil is called secondary. Okay, and hence what happens is you connect it to a AC source. So let's say this is the power station. Okay, so and then what happens is there is something called electromagnetic induction which takes place, and it induces there. So when this appears to be a solenoid, isn't it? So when there is an alternating current flows through this, what happens? There is an alternating magnetic field which is produced in the core. Now that magnetic field is linked to this magnetic field. So that what happens is the magnetic field lines flow like that. Let me have a different color to illustrate this. So what happens is the magnetic field lines are like that. They flow like that inside the core. Inside the core. So now what happens is, as the current fluctuates, the magnetic field fluctuates. The magnetic field fluctuates, and hence the magnetic field connected to the secondary coil fluctuates. And as it fluctuates, it induces a current inside this coil. Okay, so let's say if there are N1 loops here and N2 loops, and in one turn, let's say the voltage was E1, and here one turn voltage is E2, then it is said that N1 E1 is equal to N2 E2. Okay, so hence E2 will be nothing but N1 by N2 into E1. So if you want to step up, that means if you want to create this this voltage has to be increased, or you have to step up, then basically sorry, or wait a minute, potential linked in is same, so N1 times E1. I'm sorry, wait a minute, this is not the case. Wait a minute. So what happens is, just let me erase this, not this. Yeah, so what happens is, so EMF produced in each of the loop will be same. EMF is nothing but the voltage. Okay, so each of the voltage, each EMF will be same. So hence you will get a relationship where, let's say this was V. Okay, so hence it is V upon N1 is equal to, so let's say V1, and V2 upon N2. Okay, V1. So let's say this voltage was V1 produced, and there were N1 loops, and here let's say the induced voltage is V2. So V1 upon N1 is equal to V2 upon N2. So hence, if you want to up Increase the voltage V2. What do you know? V2 is nothing but N2 upon N1 times V1. So if you increase the number of turns in N2, automatically the voltage V2 will step up, will go up. Okay, if N2 is greater than N1, then V2 will be greater than V1. This is called stepping up. And this is happening only because there is electromagnetic induction is happening here. Okay, if it was a direct current, then there will be no fluctuating magnetic field, and there is no magnetic field fluctuating, then there will not be any induction over here. Hence, DC cannot produce or cannot be stepped up. Okay, so coming back to the question, student carries out an experiment and plots the VI graph of 3 samples. So this is VI graph, but unfortunately in this question, it's not mentioned which is V, which is I. Usually, it's I equals V upon R. Right, so if let's say, acha, tell me if this is my V and this is I. Okay, this is V, this is I. So now tell me, what is the current correct order? What is the correct order if if x-axis is V and this is I? Then it's A. See, usually it's a VI characteristics are measured like that. V should be in x-axis, I should be in, because this is the response to this cause. Okay, so hence let's say if you have this, now the slope here, slope here is 1 upon R, isn't it? Because I is equal to 1 upon R times V, so slope is 1 upon R. So higher the slope is high, R will be low. Okay, so with resistance R1, R2 respectively as shown in the, which one of the following is live? Nichrome wire, in which one? So basically, it means which one of the following is live? Student carries out an experiment and plot VI graph of 3 samples. It should be least resistance. Which one can be used in the live wire? Meaning is that. Yeah, Rushil, if VI graph is usually plot like that, I versus V, otherwise it will be, so hence be careful. They would give you the units here. Either if they mention V, then automatically this is VI like that. But usually VI graph, we don't say IV graph actually. We call VI curve only, but this is how, because this is the response to this voltage. Okay, so the response is always plot on y-axis and the cause on the x-axis, or input and output like that. Okay, so hence if higher the slope, R will be least. So R1 is the least resistance. Okay, R1 is the least. So hence, if you see, this option should be correct. Okay, next question, please. Okay. Do this. N resistors, each of resistance R, are first connected in series and then in parallel. What is the ratio of the total effective resistance of the circuit in series? This is in series combination and parallel combination. Yeah. The second question is a wire of length, a wire of resistance 20 ohms is cut into 5 pieces and connected in parallel. Find the effective resistance. A wire of resistance 20 ohms is cut into 5 pieces and connected in parallel. Find the effective resistance. Yeah, n square is to 1, correct? N square 1. N square is to 1 is the correct answer for the first one. So first is n resistors, each of resistance R of us connected in series. So total resistance is NR. And in parallel, so total resistance will be R upon N. So ratio will be NR upon R upon N. So N square is to 1. Okay, a wire of resistance 20 ohms is cut into 5 pieces and connected in parallel. Find the effective resistance. Four by 5 ohms. How? Shreyas, it will be N square is to 1, not 1 is to N square. Okay, so 20 ohms. So let's say R is 20 ohms. So one piece small r will be, let's say, 20 upon 5 equals 4 ohms. Now there are 5 4 ohm resistances. So 1, 2, 3, 4, 5. Okay, between A and B. How to do the previous question? I'll tell you, Mehul, just a minute. So it is how much? This is 4 each, 4 each, 4 each. So hence the net effective resistance is nothing but 4 by 5 because they are in parallel. Okay, so I hope you understood this. So 4 by 5 ohms. I'm not drawing the steps. I'm doing a little faster. Okay, now in the first case, the previous question, may pay attention. So let's say there are n resistances in series, like that. Yeah, this is 1, this is 2, this is 3, each of R. Let's say this is the nth resistor. Okay, so R equivalent in series, what is that? You simply add all the resistances. R time n times, hence total is n times R. In the second case, when they are connected in parallel, like that, and let's say this is R, 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 like that. All are R in. This is 1, 2, 3, and this is nth. And let us say I am trying to find out the equivalent resistance between these 2 points, right? So R equivalent in case of parallel is nothing but, so you write like this. So you write like what? 1 upon R equivalent in parallel is equal to 1 upon R plus 1 upon R plus 1 upon R plus dot 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 1 upon R. n times. How many times? These are n terms. N terms. So total 1 by r equivalent is equal to n upon r. I'm sorry, it's r upon n. This is correct. N upon r. So r equivalent will be r upon n. This was correct. Sorry, my bad. So r equivalent in parallel is r upon n. Now the ratio. So you have to take these two ratios in series, and let's say this is r equivalent in series, and this is r equivalent in parallel. So basically, r equivalent in series upon r equivalent in parallel is nr divided by r upon n, which is n square by 1. Understood? Let's take up another question. Okay, let's try this question. Let me see how many of you can solve this. So question is, find the equivalent resistance each is of 1 ohm but the connections are something like this. And you have to find out between A, B. Find the equivalent resistance. Ishan says it's a Wheatstone bridge. Is it? Is it a Wheatstone bridge, guys? Look carefully. Try to do it through equipotential surfaces. Because let me just put a point. Let's say this is B. Sorry, B is already taken. This is C and D. Okay, and let's say E and F. Current takes the path of least resistance. Okay, so why is it 1 ohm? Because Ishan, why is it 1 by 2 ohm? None of you are correct, unfortunately. See, think like that. Is point E or are points E and D? E and D. From the current goes through E to D, okay, and from D to B, okay. Hence 1 ohm. No. Are points E and D same electrically? Which when I say electrically, that means are the voltages at E and D same? Potential at E and potential at D same or different? Answer this question first. Are the potentials at point E, E for elephant, and D, D for Delhi, are they having the same potential? And why that would be, Ishan? They are the same, but how? What do you mean by they're the same? That means there is no resistance in between. So hence we say E and D, E and D are equipotential surfaces. Yeah, zero resistance. Very good. And similarly, C and F are equipotential. So can I now redraw this? Let's say this is my, so basically E is equivalent to point D and C is equivalent to point F and E is equivalent to D is equivalent to A and C is equal to F is equal to B. Okay. So can I now write, let's say, let us draw this. Let us say this is E and C. Okay, now this is resistance between E and C. Let's say this is R1. And what is R2? Here R2 between C and D. So between C and E was same as D. So I can connect E and D, right, as D. And C, same as C. Now there is another resistance between C and D, R2. And F and C. Now C is same here. This one. Let's say this is R3. So hence this is C and F. F is equivalent to, so this is F here. And there is a resistance between D and F. Yeah, R3. See, did I correctly do it? There is a resistance between E and C. Yes, R1. There is a resistance between C and D. Yes, R2. And there is a resistance between D and F. D and F. So this was point D. R3. All three done. And what was A? A is equal to D only, right? See above this one, A is equal to D. So this is A. And what was B? B is nothing but here. Now can you find out the equivalent resistance? Okay, so don't get deceived by the Ishan, right? 1 by 3 ohms. So then don't get deceived by the area. You just simply added it. Don't do it. Don't get deceived by the figure. Try and understand and deconstruct it and redraw and then go ahead in analysis. Okay, I'll give you one more question on that. Mm-hmm. In an exam, for how many question, how many marks that question would be, I really don't know. It will be, but not less than 3 marks for sure. Do this. R1 and R2 are in series. No, who says R1 and R2 are in series? This connection is making things different. R1 and R2 are not in series. Okay, try this one now. If any question, you can always send it to me after the class on WhatsApp. Try to solve this one. What is the value of the resistance? P, 1 ohm. Are you sure? Shreyas, 10 ohm. Shreyas is saying 10 ohm. A, 0.1 ohm. Answer is 10 ohm. What is R? V upon I. Yep. You see, what is V here? 1 volt. Or you can also find out through slope. Slope of this. Slope of this. How do I find out? R is nothing but slope of VI curve, or 1 by R is slope of I by V IV curve, whichever way you want to look at it. So this is I here, and this is V. Yeah, this is how. Oh, I'm sorry. I made a mistake. Is it? No, correct. So this is what. See, this is how VI response curve will be given. Current is a response to voltage. Now, what is voltage here? 1. And what is current here? 0.1. So hence, R will be 1 upon zero point 0.1, 10 ohm. 10 ohm. Good. One more. Confidence booster for you. Confidence booster. To wind up, confidence booster. Quickly. Three. Let's see if anyone can solve this. You'll get an award. Yes, yeah, correct. But where is the option? Yeah, there should be another E here. Can't see the values. It's 6 ohms all. All the 3 resistances are 6 ohm. All the 3 resistances are 6 ohm. Good. So you guys are good. Okay. Solve this one now. Yes, Kritika, it's 9 ohm. All are correct. Very good. Next. Copper wire has diameter of half mm, resistivity of 1.6 into 10 to the power minus 8 ohm meter. Okay, what be the length of this wire to make its resistance 10 ohm? What formula do you need to? What concept? R is resistivity times length upon area of cross section. Please be careful that this is given in mm. So please convert it into, and this is diameter, right? So hence the resistivity is given as 1.6 into 10 to the power minus 8 ohm meter, and D is given as 0.5 mm, which is 0.5 into 10 to the power minus 3 meters. So A will be equal to pi r square or pi d square by 4, which is pi into 0.5 square into 10 to the power minus 6 upon 4 meter square. You have to find out L when R equals 10 ohms, right? So let's deploy the value. So 10 equals 1.6 into 10 to the power, or let us first simplify this so that you get, yeah. So let's say, so I can say L is nothing but R into A, R into A upon rho. Okay. So hence R is given as 10. It is in SI unit. Check. Then A is pi by 4 into 0.5 square into 10 to the power minus 6. This is A divided by resistivity 1.6 into 10 to the power minus 8, and this should be in meters. 781.25 meters. That much. Let me see. So if you cut it, it will become 10 square here, and if you multiply all of them, so if you see, let's simplify further. So hence if you see, it is 10 into 22 by 7. For approximation, I can take 22 by 7, or you can take 3.14, whichever way you want, into 0.5 square is 0.25 divided by 4 divided by 1.6, and there is into 100, right? 100. So you can strike off this 100 and cut this decimal. Okay, so hence it becomes 22 into 250 upon 7 by 16, 6.4. So 6.4 can be written as 64, and I'm put a 0 over here. Okay, so this amounts to, you'll have to do the calculation into where 64. Yeah. Why are you getting so much, Ishan? I am getting something else. Let's check the calculation once. So 22 into 2500 somewhere around 120 meters. Yeah, this is nothing but this will be the answer. Okay. Yeah, somewhere closer. So something like that. And how much does the resistance change if diameter is doubled? If diameter is doubled, area is doubled. No, diameter is doubled, area is quadrupled. So area becomes 4 times. So hence the resistance will drop by 4 times. Isn't it? If diameter is doubled, decreases 4 times. Perfect. Decreases not 4 times, decreases by 4 times. So let's say R was rho L upon A. Now if D becomes 2D, area becomes 4a. Why? Because it is pi d square by 4. Area is pi d square by 4. So if you replace d by 2, area, now new area becomes a1. New area is pi into d square, or 2d by 4, 2d square by 4, like that. So hence it is 4 pi d square by 4, which is 4a. So new area becomes 4 times the original one. So hence new resistance R1 will be equal to rho remains the same, length remains the same, and A has become 4A. So hence this will be nothing but 1 upon 4 rho L upon A, which is 1 by 4 R. So hence resistance decreases 4 times. Okay. So fair enough, guys. I believe we did some problems, and in case you have anything, you can go through your entire syllabus. In case you have any other doubt related to magnetism or electricity or sources of energy, you can send it to me or post in the group, whichever way, and we'll get back to you with the solution. Yes, what I'll do is I'll post some worksheets on electricity and magnetism, so you can go through them. And I hope by Saturday, to use the Saturday and Sunday for that. Okay, and it will be done. Fair enough. So let us, call it a day, and all the best for your science test, upcoming science test. Okay. Bye, guys. So logging off. Any other question you have, you please ask me right now. Anything else? Any other question? If remaining, please let me know so that I will explain. Okay then. So I am logging off.